Hello everyone, we are back to our plasma class. So what we are doing these days, we are discussing the plasma diagnosis, and in the previous classes we have gone through the Boltzmann plot technique to determine the plasma temperature. We have discussed how this standard Boltzmann technique can be modified for axial temperature distribution, and when you are going for large volume plasma temperature diagnostics, then you have to use the Abel inversion, and how Abel inversion can be done, that we have explained. Now the another important parameter apart from plasma temperature is number density, that is the electron number density in the plasma, and you know that if it is singly ionized, then electron number density is same as ion number density, and that number density determination I will be discussing in this class. So how do we do that? You know that there is something called Stark broadening, and when we are discussing the line intensities spectrum collected, what we are getting more or less, we are getting certain lines. These are the kind of lines what we are getting, but you know that these lines are actually not lines, they do have a profile, and if you want to find out the intensity, then you should integrate this area under this curve of this peak, and then only you will be able to find out the intensity. So why this width originates, this line broadening, ideally this should be just a line, but in practice what you find, it is having a certain width. So what for this width comes, there are many there are many mechanisms by which these lines get broadened. We will be discussing that, and one of them is the Stark broadening that occurs due to electric field that is present inside the plasma. And this is one spectrum that has been recorded while the other lines were getting collected. This line what you are seeing in the inset, so this one is called H alpha line. Exact wavelength of this is 656.28 nanometer. Now probably you are wondering where from you will get this H alpha in any emission from gas. Actually, this kind of broadening can be seen for any this line that is getting generated from the system in general, but for this H alpha line, the parameters for the broadening are very well known. Okay, so whenever you use this line and you try to calculate the electron number density using this formula, using the standard formula where the constants are well known, you are pretty confident about the number density that you are offering. So and hydrogen is actually this H alpha line broadening is quite significant, that occurs when you go for the Stark broadening in plasma. So when the broadening is appreciable, then the measurement error is also less. So that is why people try to use this H alpha line for number density determination. Now again, the question comes, suppose you are doing with the argon plasma, then where from this hydrogen line will come? So for this actually what people do, they introduce a very small amount of this hydrogen in the main gas. For example, if you are using the argon gas, you insert a very small fraction, say 0.1 liter per minute kind of hydrogen into the gas, then it will basically not disturb the argon plasma because of so small quantity, but it will show the presence of the H alpha line in the emission spectrum. So once you are able to get the emission line, so the broadening that occurs in that line, that will basically be contributed by the number density of electrons which is present over there. So this hydrogen what you are introducing there is actually acting as a probe to determine the number density without significantly affecting the plasma. But if you are anyway using some gas species which are naturally containing the hydrogen atom, then anyway this line will be present. Few examples are, suppose you are working with steam plasma, so H2O, then it breaks, then H and OH, so H occurs naturally. Another thing, suppose you are working with the methane plasma, then what will happen, this H4 will be breaking and some hydrogen atoms will be released in that, so you will get naturally those things. So any hydrogen containing material, these hydrogen lines will not be a problem. Even if your this gas is having some moisture, that also gives significant intensity of this H alpha line. So that way actually you are able to know the density of the plasma without disturbing the plasma significantly. So now how the broadening works. So what you are seeing here, so these are the different lines what you are seeing, and I have expanded this 656.28 nanometer H alpha line here in the inset. What you are seeing, that this zone is expanded over here, and this is the kind of shape of the profile, that intensity profile of that line it is having actually. So this full width at half maxima, this is this width is around 0.33 nanometer. So to measure the width with sufficient accuracy, you need a spectrometer which is having that much resolution. That is, it will be able to provide you this much provide you sufficient data to construct the profile over here. So we are seeing that the spectrometer which we have used, it is providing so many data so that you can reliably construct the profile of the H alpha line. And once you have obtained the profile, then it is very easy to get the full width at half maxima. So what you are seeing here, it is around 0.33 nanometer. Now in tutorial actually we'll be telling you this one actually how you can map the temperature over a wider zone. But here in a plasma, actually if you take a snap of this this jet, you can map the spatial distribution of temperature within this. There are certain techniques that I will be discussing in the tutorial, but here what we are discussing the broadening mechanisms, because the width that you are measuring in that broadened line, it has included contributions from at least 6 type of broadening mechanisms. So I have listed some of them. That one is Doppler broadening, that occurs due to movement of radiating atoms and molecules. Then the other one is your intrinsic broadening. This is due to finite lifetime of the states. So that actually basically this comes from the uncertainty principle. This width is coming directly from that lifetime of the states. So delta t, delta E, delta t, that relationship for the uncertainty, that is giving you the intrinsic broadening. Then there is something called van der Waals broadening. This occurs due to large density of surrounding atoms in the ground state. So this van der Waals broadening, intrinsic broadening, Doppler broadening, you will find more about this in the literature. I will be showing only that part which is relevant to measurement of the number density in this case. Now the Stark broadening is of course what we are trying to measure. So that is due to presence of electric field of the charged species. And then instrumental broadening, this is specifically due to the diffraction at the slit that is happening, and there is resonance broadening something. So you get a broadening due to emitters surrounded by large number of perturbers of the same kind in the ground state. Okay, so one is emitting and it is surrounded by a large number of atoms of same type but at the ground state. So that causes the resonance broadening. So whenever you are measuring a width of the line, you should know that it is including Doppler broadening, intrinsic broadening, Van Daal's broadening, Stark broadening, instrumental broadening, resonance broadening. All of them together form the width whatever you are measuring. Now, how to separate out each of them? So that is the most important thing. So if you are able to separate out the rest of the things, then you can find out the absolute contribution by Stark broadening, and once you are able to find that, then there is a relationship between the Stark broadening and the number density. You can use that and find out the number density. So that is the basic principle. Now I come to the precise expressions for the different kinds of broadening. Okay. So now Doppler broadening, it is due to the thermal motion of the radiating atoms. So that is given as delta d delta lambda d. So that is the width of the line that is contributed by the Doppler broadening. That is equal to square root of 8 kBt log 2 divided by mc square into lambda 0. Here lambda 0 is the wavelength, central wavelength you can say. Now the resonance broadening, what we are talking about, due to surrounding atoms at the ground state of the same type, then that is related to the temperature, and it involves several parameters like you see there, the lambda r, then fr, then gr, g1, all these things. So I have just written over there what are they. So lambda 1 is basically, lambda is the wavelength, then lambda is the resonance wavelength, then fr is the absorption oscillator strength, then g1, g2 are the statistical weight factors of the ground state and the upper resonance level. So this is the resonance broadening, and then Van Daal's broadening is having the relationship that I have shown here. So it is like this, a bit complicated formula, but it involves the polarizability of the perturber. Then R is the weighted average of the square radii, and then chi is the fraction of the perturber, and mu is the reduced mass in atomic mass unit. So these are the parameters what are used here, and these parameters are available with you for the system that you are considering. From the literature you can find them out, and this T is the temperature at which you are finding this broadening. Now this temperature you have already determined using the Boltzmann-Pot technique, or that whatever the method that you have used earlier. Now here you are seeing that the instrumental broadening, there is something, so that is very particular to the instrument. When you are using certain, say, wavelength which are very precise, like say from helium neon laser you are throwing some light into the spectrometer, and then you are seeing that the width whatever it is generating in that. So from that you can precisely determine what your instrumental broadening that is occurring there due to diffraction at the slit. So therefore you can find that out, and then what you do, you need to subtract all this broadening from the broadening contribution from the width that you have measured. So the ultimate stroke broadening component comes as delta lambda 0, which is the your total broadening that you have measured, minus the delta lambda I instrumental burning minus the delta lambda van der Waal. So that again you have to you subtract the Doppler broadening as well from that. So what you find actually the net broadening contributed by the Stark effect. Sorry. So the Stark broadening what you get over here, so that is basically related to the number density as delta lambda s is equal to 1.78 into Ne by 10 to the 20 to the power 2 by 3. So once you are able to determine the absolute value of the Stark broadening, so this is not the this will be Stark broadening, okay, and this subtraction should include the your Doppler broadening as well, then resonance broadening, then instrumental broadening, all these things you should include, and then what you get finally the Stark broadening component here. So this is not be Stokes broadening, it will be Stark broadening, okay, and that expression is like this 1.78 into 10 Ne by 10 to the power 23 to the power 2 by 3. So once you are able to find out this broadening correctly, then you are able to determine the number density. So that is the basic principle behind the method to determine number density using the line broadening mechanism. So I have shown it over here. So that was the same thing what we have shown earlier. Now I would like to draw your attention about the PLT issue while you are measuring the temperature. Okay. Now, partial local thermodynamic equilibrium that holds good for the nth quantum state if prevailing electron density number per meter cube in the system maintains the relationship any greater than this expression, whatever you are getting over here. So EH is the first transition energy of the hydrogen and K is the Boltzmann constant. So if this kind of relationship is maintained, then usually the PLT is observed, that partial local thermodynamic equilibrium. And as I told you that under partial local thermodynamic equilibrium, the upper lying states are populated as per the Boltzmann distribution, but not the lower lying states. So that causes the Boltzmann plot when you get like this, it should be a linear plot, but when you go to the transition that involves the energy levels which are lower lying, they are many of the times not populated as per the Boltzmann distribution. So in this plot what you are seeing here, that this is the increasing energy of the upper states, and this is the quantity that we plot in the Boltzmann plot in the y-axis. So when you plot this, you see that these upper lying states which have this transition involves the upper states at higher energy level, they are not creating any problem. They are all falling as per the Boltzmann rule. But when you are going to the lower lying state, see the energy is coming down over here, you are seeing that this wavelengths. So what are these? This 1 and 2, and these are the 1 and 2. What you are seeing here, no? These are 1 and 2. So these two lines correspond to these two lines. Actually, these 2 points in the Boltzmann plot correspond to these lines, and they are not actually falling as per the Boltzmann plot. So just from the behavior that we are seeing from outside through the emission from the system, we are able to say what is happening quantum mechanically inside the system. So which levels are populated as per the Boltzmann rule or which are not. So this is a quantum mechanical phenomena, and manifestation is observed in the emission spectra. So that is how you can determine whether a system is in PLT or not. Okay. So with this, actually I will now shift to the determination of temperature and number density in case of cold plasma. Okay, so far what you have seen, it is a non-invasive technique. So you are determining the temperature and number density using spectroscopy. So emission spectroscopy, and you didn't have to insert anything inside the plasma like any probe, because it was also not possible, because the moment you put inside, it will be just ablated. It will be become vapor and it may become plasma. So there is no question of inserting such thing, but you can measure the temperature non-invisibly, just collecting the spectrum from particular zone and analyzing the spectrum. So that what we have studied so far. Now we are entering into the cold plasma diagnostic for temperature and electron number density. But the advantage here is that because the gas temperature is low, we can insert any probe. Of course, there is a possibility that probe itself will disturb the plasma, but if we are able to minimize that, then with sufficient accuracy we will be able to determine the number density and temperature of the cold plasma. So we come to that, we studied. There is something called Langmuir probe measurement. So even though you are not a plasma person, you might have heard about the Langmuir probe. So how they look? So I have shown some of them. So they are usually planar in structure at the tip. They are having some tip at the top. Then there is a conducting wire that is at the that goes through, and then that is surrounded by some insulator. Now these are the type of probes. This is a planar probe, this is a cylindrical probe, and this is a spherical probe. So different types of probes are used for different type of applications, but this planar probe are used extensively in plasma diagnostics, and the results that you got using this planar probe are widely used, and they are quite accurate. So I will show you some of the results that you have obtained and how the collected signals differ with spherical, cylindrical, and planar probes. That also I will show. Now, a typical configuration to determine the temperature using Langmuir probe goes like this. So there are two electrodes between which the discharge is taking place, and you have created a non-equilibrium plasma or a cold plasma inside this device. Now what you are doing, you have inserted the probe at some location to determine the temperature at that zone. Now electrons are moving in one direction and ions are moving in other direction, and what you are doing, actually you are applying a bias in the probe. So you can make the probe very negative, or you can make the probe positive. So when it is negative, definitely the electrons will be repelled. When it is positive, the electrons will be attracted, and we will note the current that is passing through the probe under different biasing condition. So you can say that this is one of the simplest type of diagnostics that is useful for plasma. So just you insert a probe, very thin probe. I will be coming to the details, the dimensions and materials that are used in construction of the probes. So you will be very much clear about how to make them. But this is just you put the probe inside and bias it and collect the current, analyze the current, and get the information about the number density and the temperature. So here you go. Actually, the Langmuir probe dimensions are like this. So it depends on the application. When the application is laboratory plasma, the probe tip diameter is of the order of say 0.1 to 1 millimeter, and probe length is say 5 to 20 millimeter kind of thing, and it is made of usually tungsten or another refractory material basically that you use for that. Then for fusion plasma, fusion devices like tokamak, your probe tip is 0.5 to 2 millimeter typical diameter, and probe length is 5 to 30 millimeter, and often it is retractable or swept for safety, because The fusion plasma involves very high energy particles. They can damage if you have kept it for prolonged period. So it is retractable usually, that is made like that for fusion devices. And for space plasma, these satellites you are sending or your space vehicles are going to space. So for that, the probe tip diameter that is used usually 1 to 5 millimeter, and the probe length is several centimeter and must withstand harsh environment that you may face. That space re-entry vehicle simulation, that ablation of the surface layer. So when it undergoes severe friction with the atmosphere, it must withstand the harsh environment that is created that time. Now, RF plasma, radio frequency plasma at low pressure. So this is there the probe tip diameter usually very thin, 0.05 to 0.5 millimeter, that is used there, and probe length is usually 2 to 10 millimeter, and may require shielding to reduce the capacitive coupling because you are using RF plasma. So this is the typical dimension. Now you are familiar that probe tip diameter is quite small. What we are using, it is 0.1 millimeter to 5 millimeter, that has been varied here as we are seeing depending on the kind of application. And probe length is usually it is not that small anyway, but it is 5 millimeter to several centimeter as we are seeing in the chart. So depending on the kind of application. Now, Langmuir probe material, as I told you that it should be refractory material. Now, the kind of condition that we expect for this kind of material is that it should have high electrical conductivity, high melting point, chemical and thermal stability, and mechanical durability. So these are the properties that we require for the material to construct a Langmuir probe. Now, the material typically used are tungsten. Advantage is that it is having high melting point and stable in plasma, but the problems are they are brittle and expensive. One thing that tungsten is used in very often used in this Langmuir probe material, used as a Langmuir probe material in many applications. Now molybdenum, this is hiding actually, so this is actually molybdenum, MO. So they are good in thermal and mechanical properties, but they have bit lower melting point than tungsten. Now graphite also is used sometime. They are chemically inert and they are heat resistant, but they have lower conductivity and can sputter. Now platinum, they are very good inert, and they are excellent for precise low temperature probes, but they are very expensive. As you know, this platinum is very expensive, and they have also lower melting point compared to tungsten. Now stainless steel, they are cheap, easy to machine, you can easily fabricate, but they have lower thermal and chemical resistance. So these are the material that you can use for. So mostly you can use tungsten for construction of such probes for average measurements. Now, what is the principle of Langmuir probe plasma diagnostics? So basic idea is that you insert a small metal electrode in the form of a wire, spherule or plain plate inside the plasma, and dimension I have already told you. Make a complete circuit and bias the electrode as I have shown you there in the diagram. So probe current can be determined using an oscilloscope, and plasma parameters can be determined by loading the probe with various voltages, positive and negative. When you are applying a high negative bias, then the probe being at negative potential with respect to plasma, electrons will be repelled from the probe, and the probe will derive a space charge, positive space charge limited ion current. Okay. So what is this space charge limited current? If you have already read the Child-Langmuir's law, that 3-up law, that is VI in the VI relationship between the 3-up they follows. So they are not exactly like Ohm's law, where V is proportional to I, V equal to IR. Here actually you will get that a nonlinear relationship between V and I because of the space charge that is accumulated in front of the probe. And in the region of strong negative voltages, the current collected by the probe varies only slowly with applied voltage. Now, probe current that time is Jp is equal to Ji, where Ji is the ion current density. So, this probe current density what you are getting Jp, that is contributed by the ion alone. Now, we should tell you that how the characteristic typically varies and what zone we are talking. So, when you are putting the negative bias like this, and when you are applying the positive bias like this. Okay. Now, we will discuss more on this, and we will go for less negative bias and then zero bias and then positive bias. So, we will discuss all these things in the next class. So, we just stop here and we will continue the same discussion in the next class. Thank you.